In this video, we're going to talk about optimization problems using calculus. So I wrote down these 7 steps. So let's just quickly go over those so we have a good overview of what's coming in this lesson. So first off, the steps needed. You have to identify an objective function and sketch it if possible. For example, if something says you want to create a garden that is a rectangle in shape, that is your objective function, to create this garden, and they're usually going to ask you to maximize the area or something like that. So your objective function, whatever this might be, that's going to be the job you have. So this is your job. What is the problem asking you to do? That's your objective. That's your objective in solving the problem. Sometimes we're going to have a constraint. So you have some limitations. So think about either a quantity that is constrained, some dollar amount that's constrained, something that is putting a limit on you. That is called a constraint, and you're going to use that with your objective function. Many times in this scenario, you're going to find that the objective function is going to have 2 variables, and you're going to use your constraint to present your objective function in only 1 variable, because we're going to take the first derivative of it with respect to that 1 variable. Don't be intimidated by the word optimization. Optimization just says figure out where this function is either at its highest or its lowest. So we're looking for a place where the tangent line drawn to the curve in question has a slope of 0. So if it's a max, it'll be downward facing like this. That has a slope of 0 right there. If it's a min, it'll be upward facing. That is a slope of 0. So you're going to use your new objective function, which is the one you got from using your constraint to eliminate one of the variables, and you're going to take the first derivative and set it equal to 0. So you're just going to get our critical value, which we've done over and over again. You're going to use a sign chart, if you like, or some other analysis to figure out, have you really found the min or the max? I find the easiest thing by far is to use the second derivative test. So second derivative test tells you right away if it's a positive when you plug in your critical value, then it's concave up, and that means you have a min. If it's a negative when you plug in your critical value into the second derivative, then it's concave down and you have a max. So make certain to check that so that you know you have found the right answer. Whenever possible, sketch these problems so you can see what they're asking for and what you are trying to analyze. Make certain to answer all the questions. Sometimes you do a lot of work and never actually answer the question. So those are some overview. Let's do a very basic problem to start off with. Okay, here is a typical optimization problem. So this says optimization problem, maximizing area. So I already know that that's my objective. So let's read the problem. Find the dimensions of the rectangular garden of greatest area that can be fenced off using 300 meters of fencing. All right, so let's see. I would say that find the dimensions of the rectangular garden of greatest area is going to be my objective function. Okay, let's change our color of our highlighter. Let me go to green. All right, let's see what color we're going to go to. Yellow. Okay, let's do that. Okay, fenced off using 300 meters of fencing, that is your constraint. Okay, so we've identified the constraint and the objective function. So now we need to get a sketch going. So let me just make that look a little cleaner. But we do have objectives and constraints. Let's do a sketch. I see that I'm going to make a rectangular garden. So here's a rectangle. Let's label the rectangle. So let's make this X, This is going to be x because rectangles have parallel congruent sides. And here's y, so here's y again for the same reason. So objective function, they want us to find the dimensions that results in the garden of greatest area. So area equals, looking at my sketch, area equals x times y. Okay, so notice right away there are two variables. So I know I have to use my constraint to eliminate one of the variables. So my constraint I'll do in a different color. So here's your constraint. We're going to say I have 300 meters of fencing. Well, I have two x's, so x here, so that's 2x. Then I have two y's, and that has to equal 300. That's my constraint. So how can I use this constraint in my objective function? Well, why don't we eliminate the y? So let's bring the 2x over. So 2y equals 300 minus 2x, but I don't want 2y, I just want y. So I'm going to divide every single term by 2, and I get y equals 150 minus x. Okay, so now let's go back to our objective function. So I'll switch to black again. Our objective function is area, and it equals x. And now I'm going to put in the constraint for the y. So I'll put that in as red initially. So this is going to be y is now 150 minus x. Okay, so now let's clean it up, and I'm going to eliminate the other color. So my objective function is 150x minus x squared. That's my objective function, and my job is to find the first derivative of this parabola and figure out where it is maximized. So take your first derivative, a prime equals 150 minus 2x. Set that equal to 0 to figure out where the slope is 0, and what I find is that x will equal 75. Okay, so I'm going to, I guess under here I'm going to take the second derivative, which will be negative 2. Okay, if I had an x here, I would plug in the 75 because I found that x equals 75. But since I don't have an x, what I see is no matter what value I have for x, my second derivative is negative, and therefore I have found that I've maximized the area. So the answer is not complete as of yet. I know that x is 75, so here's x, 75. How do I get my y? Well, look right here. Here's an equation for y. Take your 75, plug it in for your x, and I'll change to red again, and we get that y equals 150 minus the 75, so y equals 75 also. Now we don't need to test this because we've tested the x in the second derivative, and we know that whatever x we find helps to maximize the area of the rectangle formed. So we always know right away then that the y is going to do the same. So my dimensions, so my answer, my dimensions are that the garden will be 75 meters, make sure you use meters, the units this time, times 75 meters. So that's going to be your answer for the dimensions of the rectangle garden of greatest area. That's going to be fenced off by these 300 meters of fencing. So that's your basic optimization problem where we found a maximum. So make sure you understand these steps, and then we'll go on to another problem as well. Based on this, you should be able to do the 1 to 10 in the homework assignment. So let me go to the next page of notes, which will be the day 2 of notes. our next problem asks us to optimize a problem in maximizing the area. So it says find the dimensions of the rectangular garden of greatest area that can be fenced off using 300 meters of fencing. Okay, so let me just, let me correct myself. That's the same thing we just did. So let me grab another picture for you, and then I will start again. Okay, that's better. So optimization problem, minimizing cost. So before we maximize the area of the garden, now we're going to take a similar garden and we're going to minimize the cost. So we have to think about what we're doing here. It's going to involve not one sketch, but probably two sketches. So I read it out loud to myself and I say a rectangular garden of area 75 square feet. Okay, the 75 square feet is a constraint. Is to be surrounded on three sides. So three sides are brick, and that brick costs $10 a foot, and on one side by a fence costing only $5 per foot. Find the dimensions of the garden such that the cost of the material is minimized. So my job is to minimize the cost. So I'm going to do my first sketch, which will incorporate some cost ideas. So if I say that this is, I'm going to make this y this time, this is y, and this is x, those would be the dimensions. Okay, these are just plain old dimensions. Now let's do the same idea, but now I'm going to involve some costs. So this is just the area. Here I'm going to incorporate some costs. So I know my lengths and my widths are still the same. So let's think about this. It says the garden is going to be surrounded on three sides by a brick wall costing $10 per foot. So for every foot, this one will cost $10, that'll cost $10, that'll cost $10. So those are the three sides. So that'll be my brick. Okay, so let's just make believe that this is kind of red. So it's my brick. Okay, so we make this a little darker. Okay, so this is 10y. Alright, so now the other side is just a fence, and that only costs $5. So that's going to be a 5y. So I have the brick, and I have the fence. Okay, so my objective is to minimize the cost. Well, what will the cost equal? Well, the cost will equal 5y plus 10y, so I can add the y's together, that's 15y, and then plus 10y plus 10y, so that makes that 20y, and that's my cost function. Now, what's the constraint? Well, look back up here, so I'll change colors again. It says a rectangular garden of 75 square feet is to be surrounded. So the pink is my constraint. So the constraint is the area of the garden. So I'm going to use this. This is the area of the garden. And I'm going to say, what does that area equal? Well, that area is going to equal x times y. But it's more than just x times y. I already know that the area equals 75, so I do not need to add another variable. So I'm going to take away that variable, and I'm going to make this 75. Alright? So now what I can do is I can say, wait a second, my objective function has two variables, and that's going to cause me a problem. So, and I've written this incorrectly, haven't I? So I should have 20y. So let me go back up here, and in case you had not caught that little mistake, let's get that squared away. So I'm going to erase that, to see how this should have been a 20x. So I'm going to make that an x. Okay, so that's good. So now, why don't we replace, let's replace the y's. So if I see that 75 equals xy, then what do I know? I know that y will equal 75 over x. So I'm going to use this to replace my y. So let's write a new constraint, and this is our new objection function, only in one variable this time. So c is going to equal 15 times, and I'm going to have the y replaced by 75 over x plus 20x. So if you do the math, so 75 times 20 is what? I misspoke. I wanted to say 15 times 75. So 15 times 75 should be 1125. So 1125. And then take your x that was in the denominator and bring it to the numerator. Okay, plus 20x. So I haven't taken any derivative yet. This is just my cost function. So now take your derivative and you should be getting negative 1125 x to the negative 2 plus 20. Okay, if you solve this out, you will get the fact, let me see if I can do it for you. So let me find a place to do it. Okay, so I just pulled this to the next page just to have some more room. So what happens next is that I'm going to set this equal to 0, so then I'm going to get 1125 over x squared equals 20. So 20 times x squared equals 1125. X squared equals 1125 over 20. And I look at this and I realize I can reduce it by dividing the numerator and the denominator by 5, excuse me, and I get this. Now, I don't want x squared, I want x, so x will be plus and minus, and the square root of 225 is 15, and the square root of 4 is 2. Okay, so x equals plus and minus 7.5. Now, I can't have a negative length, so x will only be positive 7.5. Okay, so that's my x value. So again, I'm trying to figure out the dimensions of the garden such that the cost of material is minimized. So far I have that for my x. Now what you absolutely want to do, and I'll do it up here, so I'll change colors. Let's do it in orange. Let's take the second derivative and make sure that we're actually aiming to have a minimization of the costs. So take your second derivative, and I'm going to get negative 2 times that, so 2250 times x to the negative 3. So c prime prime equals 2250 over x cubed. That's going to always be positive because my x value has to be positive. So therefore I have discovered that the x value I've solved for does indeed give me a minimum cost. Again, I'm looking for the dimensions, so I know that, and I'll change colors again so that you can see what I'm doing now. So I know that we're looking for dimensions, and we knew that our constraint was 75 equals x times y. So if we already know that x is 7.5, then we can solve for y using our constraint, and that's the way we're always going to solve for y, going back to your constraint. So I end up with y equals 10. So what are my dimensions? And do I have units? Yes, I do. It is in feet. So it looks like it is going to be 7.5 feet times 10 feet. So those are my dimensions. So that is my answer to this problem, because I went back up and I said, what do they need to find? And they wanted to find dimensions. So that is my answer. They could have also asked me how much it would have cost. If I wanted to do that, I would go back and I would figure out if I plug in for my x's and my y's, I could then add that up and I would determine the cost. I have not been asked to do that, so I'm not figuring that out. But this, my point in looking at that feature is that I could ask you several questions as a result of all your work on this problem. So always, always, always go back and figure out what questions they're asking and make sure that you have indeed answered it. They also could have asked you how much the fence cost, how much the brick cost. There are a lot of questions that you could have easily been asked, so make sure that your work completes the problem, whatever it might have been. All right, we're going to do the last problem on the next page. All right, in this problem, they've asked us to minimize surface area. So remember, with optimizations, you can do minimizations and you can do maximizations. You will not know what it is you're doing until you take that second derivative and evaluate it for the x that you've just solved for by getting the critical value. So it's really important to recognize that the approach is always the same, but you have to take that second derivative in order to know that you are doing what they are actually asking you to do. So let's read this. It says a canvas wind shelter for the beach has a back, 2 square sides, and a top. So it's pictured here. Find the dimensions for which the volume will be 250 cubic feet and that requires the least possible amount of canvas. Okay, least, that word least is your tip-off. That's your job. Your job is to minimize the surface area of the canvas. What is the surface area? It's the area of each of the surfaces that we see. So there's no bottom. So let's figure out what our surface area would be. Well, what's the surface area right here on the top? That's a y by x. So surface area so far, I have y times x. Okay, how about let's change colors. And what's the surface area of the sides? So they are x by x, and I have 2 of them. So plus 2x squared. Okay, we have one more surface area. And that last surface area is the back panel back here. And what are its dimensions? It looks like it's also an x times y. So plus another x times y. Now I can combine those two x times y's, and I can say that my surface area, once I combine all my terms, is going to equal xy plus xy, so that's 2xy plus 2x squared. Now that's my objective function, but notice it's in 2 variables. Now think about your constraints. The constraint is that the volume, so the volume has to be 250 cubic feet. So what is volume? Well, volume equals length times width times height. But we certainly don't want to introduce 3 new variables. So let's look at our picture. And volume is going to equal, length is y, I guess that could be width too. So the 3 variables will be y times x times x. So that's yx times x is x squared. And I don't need to keep volume in there because I know it has to be 250. So really my constraint is that 250 equals y times x squared. Now, that's my constraint, but we're going to use the constraint to eliminate one of my variables. I think the easiest thing is to eliminate the y. So it looks to me like your y is going to equal 250 divided by x squared. And we're going to replace this y over here to make our new objective function, which we'll do on the next page. Okay, so let's continue writing this objective function. So now I have my y replacement, which is going to be, I'll just use parentheses, 250 over x squared plus 2x squared. All right, now let's clean this up. What can I do? Well, 2 times 250 gives me 500, and then, oops, what did I just do? Hang on. Okay, 2 times 250 gives me 500. So I just took care of this and this. Then x divided by x squared is going to be x to the negative 1, because I canceled an x and brought the other x up. Okay, plus 2x squared. All right, that's my objective function written in one variable. So now I'm set to take the derivative. So notice how much work you have to do now to get to the situation where you can take a derivative. Our job is to minimize the surface area. So I'm going to take the derivative and I get negative 500 x to the negative 2 plus 4x. That's my first derivative. I'm going to take my second derivative because I know I need to have that anyway. So that's going to be 500 x cubed, x to the negative 3, excuse me, plus 4. So what do I know about that? Well, I know my x has got to be a positive measurement. Since my x is going to be positive, this whole expression will be positive, and therefore I will have minimized my surface area by solving for x from the first derivative set equal to 0. So when I solve for x, I get, so let's make a box over here so we can do that. So I have 500 over x squared equals 4x. So that's going to mean that I get 4x cubed equals 500. Divide both sides by 4. X cubed equals 125. Therefore, x equals 5. Okay, so x equals 5. What is my job? My job is to find the dimensions. So far I have one dimension. I only have 2 dimensions, so I'm doing pretty well. Don't I know from this equation right here that my y equals 250 over x squared? So let's calculate our y. Y is going to be 250 over x squared. That would be over 25 since x is 5. So y is 10. So my dimensions, and this will be my answer, the dimensions will be, to minimize the surface area, 5, and do I have units? I do. 5 feet by 5 feet by 10 feet. Okay, that's my canvas that I'm going to be using. 5 by 5 by 10. So these are the basic problems that we'll be tackling in this homework assignment. There are more complicated optimization problems, but they build on this theme. So you want to absolutely go back and make sure you understand why I'm doing what I'm doing in using both the objective function and the constraint, and how I know that I either have a max or a min. It's by that second derivative test. Be comfortable with all of those things because you have to know this in order to do the more advanced problems.